My name is Tim Linden. I am a first-year postdoctoral fellow here at the University of Chicago. I am filling in today for Lise Jennings, who is going to be your normal speaker for most of the course this spring. She is at a conference somewhere. So I'm going to talk today about the hunt for dark matter, which is the second in our part on exploring this expanding universe. So the first thing I want to talk about, though, is go over shortly what was done last week, and just cue you in on a few main points because everything links together in astrophysics, and so some of the things you heard last week will become very important into what I'm talking about today. So just a couple key slides to remember. First, we have an expanding universe. Edwin Hubble in 1923 and then 1929 showed that the further away a galaxy is from us, the faster that galaxy is moving away from us. The universe is expanding, and not only is expanding, we later learned that expansion is accelerating. So galaxies that are far away, way out here at hundreds of thousands of light years, hundreds of millions of light years, are moving much faster away from us than the galaxies that are closer. And that tells us the universe is expanding. And something that happens when things are moving away from us is that the light from those objects is redshifted, which means that the wavelength of the light is stretched towards lower frequencies, higher wavelengths, and objects that were, say, white start to appear more red in the visible spectrum. And that happens not just for light that we can see in the visible spectrum, it happens for X-rays and radio waves and microwaves and everything that is a photon. And one of the earliest pieces of light that we see in the universe is this cosmic microwave background, which is a microwave level of photon. So it's less energetic than visible light, slightly more energetic than radio waves. It happens to be very close to the same frequency that your microwave oven uses. And it turns out that any direction we look in the sky, we have this map here that points out different directions folding in for the whole universe, we see almost the same radiation. And that's interesting for a number of reasons, which will be one of the main things that people will keep referring to this over the course of this lecture series. But when you look very closely and very fine-tuned, even though this looks approximately the same everywhere in the sky, you start to see what we call anisotropies, or different patches that are either a little bit hotter, where it's red, or a little bit colder, where it's blue. And by hotter and colder, I mean that the average photon is either slightly more blue, hotter, or slightly more red, colder. So those are the couple main key points that you learned last week. So now what is dark matter, right? This is going to be another piece of our cosmic puzzle. This is going to be another piece of understanding the expanding universe. So first, let's say, what is matter? Matter is anything that has mass and attracts other objects towards us. You're matter, the chairs are matter, the Earth is matter. They all have a gravitational force that they exert on every other object in the universe. And how do we know how much matter or mass is in our universe? Or let's just focus not on our universe at first. Let's focus on our galaxy. How do we know how much mass is in our galaxy? Well, you see stars move around the edges of the galaxy, right? And stars move because they move in circles because they're moving straight at any time, but then there's a force, gravity, that's pulling them in towards the center of the galaxy. And it's just like when you used to be on I now forget what these things are called. Thank you. When you were little, and the faster and faster it spun around, the harder you had to hold on, right? You had to use your hands to make more force to pull you in so that you didn't fall off the edge. Now, it's the exact opposite, or going the exact opposite way. If I know how fast I'm spinning around, I know how fast I have to pull on to stay on, right? And so I look at stars out here, and I see how fast they're spinning. And I say, how much pulling has to be done from the center of the galaxy in order to keep them in a circle when they're moving so fast, right? That's how we find out how much mass is in our galaxy. So we add up then we get that number, and we add up all of the mass that we can see. We add up all the stars, we add up all the gas, we add up all the dust, everything that we see in our galaxy today. We add it up, and it's not big enough. There's not enough matter, not enough mass in our galaxy to hold the stars if they're moving as fast as we see them move. So, in a bit of imaginative naming, because physicists make the best names, we call all the matter we can't see dark matter. And that's what dark matter is. At its simplest, it is extra mass that's in galaxies, and it turns out in everything else, that makes things move faster in circles. So this was first noted by Fritz Zwicky in 1933. He's there looking surly. That's an important part of the puzzle in that Fritz Zwicky always looked surly. And so when he first noted that different galaxies, he didn't look at stars first. He looked at big clusters with many galaxies and found that the galaxies that were moving around the clusters were moving faster. But Fritz Zwicky came up with 1,000 really interesting ideas. About 5 were novel and correct and groundbreaking, and the rest were not right. And because he was surly, nobody followed up on this for a long time. Until Vera Rubin in 1969 looked at the M33 galaxy and did the same thing with stars moving around it. And what she saw was this. What she expected, she looked at all the light and expected that, as you got farther and farther away, there wasn't much more mass. And so gravity gets weaker when you're farther away from an object. And so stars that are farther and farther away from the center of this galaxy should move slower. That's what she predicted. And that's what everybody predicted who had looked at a galaxy. But when she looked at the stars and how fast they're actually rotating, she saw that as you moved farther and farther away, the stars kept moving very fast and actually moved a little bit faster. Right? So out here, we expected the stars to only move at 50 kilometers per second, and instead they're moving, well over 150 kilometers per second. There had to be more mass to hold stars that are moving that quickly. So we have dark matter. There's something. There's something else that has to be there. And how much dark matter is there? It turns out that in our galaxy, the dark matter mass is 1 trillion times as massive as our sun, as a point of comparison. But if I add up all the stars and everything else in our galaxy, it's only 90 billion times as massive as the sun. So there's about 10 times as much dark matter in our galaxy, the Milky Way, as there is visible matter. And if you go over the whole universe, and I think you saw this picture last week, you find out that only 0.4% of the total mass in our universe is formed of stars and other things that are very bright. About 10 times as much of that is what we call intergalactic gas. That's mostly hydrogen or helium atoms. They haven't collapsed to form stars yet, but there's a lot of this gas out there. But that's only 4%. 23%, about 6 times as much, is dark matter. This extra mass that influences how galaxies and clusters of galaxies form, but doesn't emit light. And 73% is what you'll be talking about for most of the rest of this, which is called dark energy, which is something that I think every other lecture will go into, and I won't talk about too much today. So, what is dark matter? All we know is it's something that doesn't emit light. And before we go off and create new particles and new theories of physics, we're going to do that eventually. But before we do that, let's make sure it's not something mundane, something that we experience in our everyday life. Maybe it is just gas or dust. We're miscalculating gas or dust. How do you see gas if it's thousands of light years away, right? Well, this is how you do it. You look for a star, right, and you know kind of how stars emit. They're black bodies of a certain temperature, and you know exactly what the spectrum of that light from a star should be. But if the light has to move through gas, then the gas absorbs some of the light. And it absorbs light in a very specific way. As those who may have taken chemistry know, there are certain wavelengths of light that are absorbed very efficiently by hydrogen gas because they correspond to moving electrons around in the gas, which is a technical detail you don't need to know. But it's the same thing as, say, a neon lamp. When you see the yellow lamps that are outside on streets, they emit a very specific frequency of just yellow light. It's not light on a continuum that looks yellow. It's just a yellow frequency of light. So the same thing happens for absorption, and hydrogen gas absorbs this wavelength and this wavelength very, very efficiently. So if you looked at a star that was moving through gas, you would expect to see this, and instead you'd see this with gas, where the gas very efficiently absorbs the light. And all different gases create different absorptions. So this is some water absorption. This is, I don't know what that is. This is carbon. So you would see, looking at a star, you would see all these characteristic dips that tell you how much gas and what type of gas is in between you and the star. And so you look at all the stars in the Milky Way. You say, that's how much gas is between us and that star. You add it up, and you don't get enough gas, right? You get that 3.6%. You don't get the whole 24%. Okay? Maybe it's something like planets. Planets don't make their own light. They have a lot of mass, and they're hard to see. How do we know that there aren't just thousands of planets floating around our galaxy, or millions of planets, and that this makes a lot of extra mass? Well, so what you can do is you look again at stars. This is a repetitive thing. Look at stars. They make a lot of light, so they give us a lot of information. And if a planet's in the way, the planet will block some of the light from the star. And it turns out you don't just need like thousands or millions of stars in our galaxy in order to make the dark matter. Jupiter is only 1/10,000th as massive as the sun. So if you want 10 times as much as all the star mass to be dark matter, you have to have 100,000 planets per star. Lots and lots of planets. So what you would see is this picture. You have a star there, and a planet moves in front of the star. And I'm seeing how bright is this star as a function of time. You see every time the planet moves in front, the light from the star gets dimmed, right? Because some of it gets blocked by the planet. So you look at all the stars and you say, how many planets can there be without just seeing these things all the time? And it turns out there can't be enough planets, or there can't be enough asteroids, or any other rocky body that would cause stars to dip in luminosity and come back up. So these are kind of what we call machos in general, massive compact halo objects, or massive compact objects. And you can, for any kind of mass of the object and number of the object, you can say how much light should be blocked from stars, and it's always too much. So it can't be planets. Okay? Maybe it's something like black holes. Black holes are way more massive than planets, so I need fewer of them. Maybe I need 100 million black holes instead of 100 trillion. I don't know. You would see the exact same story as I just said with planets. I would have some object behind, right? And the light would get blocked by the black hole. But only a small amount of the light would get blocked. What would actually happen is light that wasn't going to come to me, it was going to go this way, over here, gets pulled by the black hole into a new, black holes can actually affect the direction of light. They're so massive. So what I would see is light that was going to go this way and light that was going to go this way, both coming back, being pulled and being focused on me. So here's a star with a black hole in the center, and now the star is stretched out into this little circle like this. Right? Light that was going to miss us on that side and miss us on that side got pulled back, and we see this what's called an Einstein ring, this bright ring of light. You could watch this happen in this simulation. This is a black hole moving with a galaxy behind the black hole. This is way nicer than anything you'd actually expect to see in the sky, and the black hole is moving really fast. But what you would see, right, is this galaxy gets warped, and in a very characteristic way. And you can watch the stars kind of rotate around in a way that you would see. So you can do your analysis. How many black holes could there be? And it turns out there can't be that many black holes. Not enough to make the dark matter. Okay. Pretty exciting. So we've rounded up all the usual suspects. Everything that was supposed to make mass that we wouldn't be able to see, we tested, and it's not anything normal. So science takes us in interesting directions. Before we go to crazy land, real quick, let's make sure that we're actually confident in this prediction. Maybe it's not that there's extra mass. Maybe we, for instance, don't know how gravity works on really long distances. We know how the gravity works between us and the sun, maybe, but when you go out a whole galaxy, maybe it's stronger or something like that. Or maybe we're really miscalculating something. So let's look for some other hints that there's really dark matter everywhere in the universe. And a couple appear, and most of these actually within the past 20 years or so, which is exciting. First is what's called the bullet cluster, which I think was discovered in 1996, but don't quote me on that. So that is two massive, what we call clusters of galaxies. And clusters are very bright groups that have thousands of galaxies in them each. And these two clusters of galaxies are crashing into each other at, I think, 6 million miles per hour. big number. So one is going this way and the other is going this way. And what happens when two massive clusters of galaxies crash into each other? Well, galaxies and even clusters of galaxies are mostly empty space, right? Our sun is very small, and the distance from the sun to the next star is 4 light years, which is a crazy distance. So stars mostly don't actually hit each other. They mostly just pass right through to the other side. They're moving so fast that they just kind of keep flying through. But gas, on the other hand, there's lots of gas in its particles, and gas can collide with each other very efficiently. So the gas, as two clusters of galaxies merge, will crash and it'll get kind of stopped in the middle, right? It'll all crash, it'll all heat up, and when it heats up in the middle, it produces X-rays. And so that's what you see. This is a 2004 image. This is what you see in X-rays, this pink hot gas. So it's color-coded pink here, but this is where we see X-rays coming from in our space telescopes. On the other hand, dark matter also doesn't collide efficiently with each other because it's dark, which means it doesn't interact with light, which we said. It doesn't interact with light means that it doesn't have an ability to exchange photons. So when I touch a table and the table doesn't let me move through it, it's because there are photons being exchanged between me and the table that say, hey, there are electrons here, and there are electrons in my finger, and they should repel each other. But dark matter can't do that. So dark matter just moves straight through. And so we calculate where the dark matter is. How do we do that? We look for this kind of, like you saw black hole lensing. Black holes make the light that comes through it misshapen. We just showed that in the past movie. Dark matter does that too in a different way. And so we calculate where the dark matter is by looking at these galaxies that are behind it. You're always looking at bright stuff behind you. And you see how these galaxies get misshapen by the dark matter. So we know the dark matter is out here where it's blue. The gas is here where it's pink. And what that means is that the dark matter is not just, we didn't just miscalculate how gas has gravity or something like that. The gravity is now out here. The gas is in here from two different places. So that means that there's a new fundamental particle that makes the dark matter that can move seamlessly through colliding galaxy clusters. So we're really looking at something new. And this is a big observation for telling us that it's a new particle. Another thing is what's called structure formation. This is kind of a complicated idea, but how do galaxies form in the early universe? Where do they form? And more importantly, how do galaxies form in relation to each other? If I have a galaxy at point A, is it more or less likely that there's a galaxy right next door to it than if there wasn't a galaxy at point A, right? Do galaxies cluster together, or do they try to get as far apart as possible? And since galaxies form based on mass and gravity, which makes galaxies collapse, and most of the mass in the universe is dark matter, dark matter really controls how galaxies form and how they form where they do. So what you can see here are two different spiderweb structures. And these are simulations of how galaxies should form just from dark matter. This is how dark matter should clump and how it should form these very bright regions and these kind of spiderweb things that move between them. And anywhere that you see bright stuff in either of these pictures, this should be where galaxies form. So right here in the center is a very massive galaxy cluster, like we were talking about, with thousands and thousands of galaxies. And then there should also be galaxies along all these little strings. This is an observation. It doesn't look as cool as the simulations. Observations are harder. This is the sun here, or the Earth, and we're looking out. And this is where galaxies form, and it's difficult to tell from these images, but they're exactly the same thing. They match very well. One of them, this is kind of a full 3D image because I have a simulation. I can do it in a computer. And now we're just seeing kind of in 2D what it looks like when we look out. This image barely fits into this talk, but it's so pretty that I always show it. This is what's called the Hubble Deep Field image, as some people might know. The Hubble Deep Field is, we took the Hubble telescope and we said, let's point at the darkest spot in space we can find, where we don't think there's anything. There's nothing from our galaxy in this patch of space. There's no nearby galaxies in this patch of space. And it's a very tiny patch of space. Here it is compared to the full moon. And we looked with the Hubble for a very long time, and this is what you see. These are, every single dot of light you see in this picture is a galaxy. Say if that's a star, you can tell by the little cross that goes through it. So you got one star and like, I don't know, 10,000 galaxies in a little patch of space like that. And these galaxies form in a very specific structure, based on this. And so, you look out in the night sky and there's information everywhere about how galaxies form and where they form, and from that, about how dark matter works. So I'll give you 10 more seconds to look at that. Okay. And the last thing, and then what you talked about last week, also matters here, is the cosmic microwave background. So again, the oldest light now. Not looking at galaxies, looking at this mostly the same everywhere light in microwaves, but with this kind of, I'm going to use the technical word again, anisotropy, just meaning that if I look in one direction, I look in another direction. It's very, very slightly different, on the order of like 1 part in a million. And it turns out it should be different in different scales. Like, it shouldn't be like this whole half is brighter than this whole half. It shouldn't be that, there should be all sorts of different correlations based on how galaxies form and where they form. Based, again, on this kind of structure formation picture here, tells us how it should be hotter and colder. And when we look at these correlations, this is what it should look like. This is our prediction from cold dark matter is this line. These are the data points. And yes, there are error bars on those data points that are way, way too tiny to see. It is a beautiful fit to how we expect galaxies to form and how we expect that to affect light that arrived and moved through those galaxies and came to us today. So it's pretty stunning. There's a fun story about this that you might not have been told last week, but I always like to tell. So the cosmic microwave background is actually, I think it was mentioned last week, very easy to see. If you tune on like your old TV, most of the static you see is actually cosmic microwave background, or a pretty large fraction of it, because it happens to be at the right frequency. And so two scientists, Arno Penzias and Robert Wilson, were making an early radio telescope in the 60s. And they wanted to look at galaxies and actually different stars. And they wanted to see radio emission from that. And they did. But it also turned out every direction they looked, they keep seeing this stack that looked the same in every direction. And at first, they thought, not dark matter or cosmic microwave background, they thought our telescope is messed up, which is a good first guess to make. And so they decided, what would mess up our telescope? Well, there are a lot of birds around. And the birds, they keep making a mess on our telescope. It's exactly what they were thinking. And maybe that's kind of messing up with the metal in the telescope. There's bird droppings all over it. So we're going to keep trying to clean them. And they tried to clean the telescope, and that wasn't working. So they installed things to scare away the birds, and they installed these traps all around the telescope to get rid of the birds. And they couldn't get rid of them. And they got rid of the birds. They couldn't get rid of the signal. And at one point, Robert Dick heard about this. And he said, wait a second, you're saying this is light and it's 2 degrees Kelvin, which is, I predicted 2 degree Kelvin light from every direction in the sky 5 years ago. The reason I predicted that is this cosmic microwave background. This is exciting. We're seeing exactly what I predicted from every direction in the sky. And now the Nobel Prizes can be handed out, and they were handed out to the bird dropping guys. They got Nobel Prizes for accidentally seeing something that they thought was birds. Robert Dick did not get a Nobel Prize, which is why you should design the experiment without knowing what you're doing. Fun story. So, now we have a particle. We think it's a new particle now because the Bullet cluster tells us it's offset from everything else in the sky. It affects the cosmic microwave background.
Wasn't Gamow that predicted the background?
There were 3 or 4 people. It just so happened that Robert Dick was 20 miles away from the experiment, so he heard about it first from some friends of friends.
Yeah.
So I used him in the story. But yeah, there were more than one prediction. That's a fair story. They should have got Nobel Prizes to a lot of them, right? Okay. So we think it's a new particle. It does all the things that a new particle should do. And what are the properties that this particle has to have? And why do I say new particle? Why don't I say some other particle that we know about? Well, it has to be dark. We defined it as dark, right? It doesn't interact with light at all, which means that most particles like electrons or protons or even neutrons can interact with a photon. which is light. And they will scatter it or absorb it or something like that. So it has to be dark. It can't interact with a photon. It has to be stable. It was around 13 billion years ago to affect the cosmic microwave background and to influence galaxies. It's still around today, influencing how stars move. So when I mean stable is it can't decay to other particles, right? It has to stick around in some way. And actually, protons and electrons that we see, everything that makes up us is pretty stable. But most particles that we know of that we can form in colliders are not stable. And it has to be cold. And what do I mean by cold? That means it really has to be moving less than the speed of light. If it's going to fall into galaxies and kind of cluster in the center or around galaxies and move things towards it, it can't be moving so fast that it just escapes the galaxy and flies on in every direction. So cold technically means that its mass is higher than kind of its velocity or its energy. So it needs to have those properties. So here are all the particles we kind of know about. All the quarks interact with light. They're not dark. Light is also light. It doesn't work. These bosons all interact with light. They're not dark. The electrons and muons, they interact with light. They're not dark. The one thing that could work for a while was neutrinos. And neutrinos don't interact with light at all. They only interact with something called the weak force, which is a weaker version of an interaction. So like, for instance, gravity is a very weak interaction. The gravity between two particles is very, very weak, the gravitational force. The electromagnetic force that makes light is very strong, relatively. And the weak force is a new force that lies somewhere in between. So these only interact via the weak force. It could work. It turns out, though, that the neutrinos are very, very light. So they have very, very little mass. And they shouldn't have a lot of energy, so they're not cold. So they're ruled out because if they were the dark matter, they would just kind of float everywhere. And you would not have dark matter clumping up to make galaxies. So we ruled out all the particles that are light. So we need a new particle. And it was thought out in the late 70s, early 80s by a number of people that this could be correlated to another puzzle that was in particle physics, not in astrophysics, called supersymmetry. And what supersymmetry basically says is that there is a correspondence between the particles we know of, all these ones here that you saw in the last slide, and particles and a more massive version of those same particles. So for instance, the up quark has an up squark. For the supersymmetric particle, you add an S. Because like I said, we're creative. So the up quark has an up squark. The charm quark has a charm squark. The electron has a selectron. So you add all of these new particles into your theory. And they don't usually interact with the standard model particles. So you won't see them normally. And it turns out that the least massive of these particles could be stable. It is in fact predicted to be stable. Because in the early universe, you would form all of these particles that we see today. You would form all of these. And just like all of the particles up here decayed into just up quarks and down quarks, which are what make protons and electrons, all of these particles would decay into whatever the lightest particle was here. And if that lightest particle doesn't interact with light, and in a lot of theories it doesn't, then it makes everything that you want for dark matter. It doesn't interact with photons, so it's dark. It's stable because it's the lightest one of these, so it can't decay to anything lighter. And it's cold because all of these are much heavier than all of these. So a little bit technical, but supersymmetry comes to the rescue. It gives us naturally the new particle, and it also solves a lot of problems in particle accelerators, which is the reason you came up with supersymmetry originally, but I'm not going to talk about it here. So it turned out that then if you had this supersymmetric particle, there was something called the WIMP miracle. WIMP miracle, because I guess we overstate our findings. And the WIMP miracle was, if I had this particle and its mass was about the mass I would predict for weak interactions, which are the interactions I want this particle to use to talk to normal matter, that are very rare, if it had weak interactions and it had a weak mass, which is a mass that's about 100 times as massive as a proton, then it would naturally, in the early universe, form the exact 24% of dark matter that I wanted it to form in the early universe. So the only thing I have right now is this question of why is there 6 times as much dark matter in the early universe, or in the universe today, compared to normal matter? If they never ever talk to each other, if I just formed some clump of dark matter right at the beginning of time, and I formed some clump of normal matter, and they have no way of knowing about each other, then why 6 times? Why not 1,000,000 times, or 1,000,000,000 times, or 1/1,000,000th of as much times, right? The fact that they're so close to the same amount indicates that they probably had some way to arrange that how much do you want of this and how much do you want of that, and exchange particles between them in the very early universe, when the universe had a lot of energy. So the Webb miracle naturally predicts that. You give it the interaction that allows them to talk to each other, and it's this weak interaction we already know about, which is nice. And you give it the mass that we already know that weak interactions have, and you naturally get out this 6-to-1 ratio, which you want. Great. So how do we detect this particle? Right? It doesn't interact with light. That makes it difficult. Because if you remember from astrophysics, what I did is I looked at stars every time. I looked for light in astrophysics, and I found stuff. And it's the same thing if I'm going to a particle accelerator. I look for light or charged particles that make light that come out of collisions in particle accelerators. How do I find this thing? Well, I did give it this weak interaction, this interaction that's weaker than the electromagnetic interaction that makes light, but it's still a way for particles to collide and produce things. So this is kind of a mock diagram here, called a Feynman diagram, to people who know, or have seen these sort of things before. So in the early universe, I needed to be able to have dark matter produce standard model particles. Basically, I had to have a dark matter particle come in, another dark matter particle come in, and 2 standard model particles come out. And at the same time, standard model particles can go the other way. They collide and they produce 2 dark matter particles. And if this was happening in the early universe, then I get about the right amount of each out, because they were able to go back and forth. So if I had too many dark matter particles at some time, more dark matter particles would collide and make standard model particles. If I had too much standard model particles, they would collide and make dark matter, and everything would kind of equalize out. Good. So if I could do that in the early universe, I can do that today. It might be harder. The universe is not as hot now as it was then, but it's possible. So I can do it in 3 different ways. I can look at particle accelerators where I'm crashing really high energy, almost at the energies of the early universe, particles together. And if I'm crashing 2 standard model particles, 2 protons together, I can make dark matter particles. Right? So I will look for those in the LHC. I can't see the dark matter itself. It doesn't make light. But I might be able to see a signature in how my collisions work to tell me that there's dark matter there. I could look for dark matter particles. It turns out with these fun diagrams is you can turn them in every single direction. You can make time basically go in every direction for what the started outcome is. And all of these processes are valid. So I could have a dark matter particle come in, and it could hit a standard model particle, say on Earth somewhere, and that standard model particle could gain energy. They could bump into each other, and I could see that bump happen. Right? Or you could do the last direction, which is you could look out in space where there's lots of dark matter, and you could see 2 dark matter particles hit each other and make standard model particles. I mean, you could see those in space somewhere. Right? So these are the 3 different experiments that are done, and they're done in different ways. You take like the LHC or some particle accelerator, and you crash the standard particles into each other to try to make dark matter. You go deep underground, and you try to see if a dark matter particle will hit your protons or hit your standard model particle, and you can see that bump. Or maybe you go out with a space telescope, and you look for dark matter particles colliding into each other somewhere in the universe. Now I'll kind of talk about these in a little more detail. So particle accelerators, you've seen, they found the Higgs boson and stuff like that. And what you look for, since you can't see the dark matter itself, is you look for 2 protons collide, coming in like this, and everything went this way. And this is, if you go and think about playing billiards or pool or something, right? If I had 2 billiard balls hit each other, one goes this way, the other one had to go this way, right? That's because I have conservation of momentum, and if 2 things bounce and go, they have to go opposite directions. Everything can't shift the same direction. So I do this in particle accelerators. And normally, if I see two particles come in from here and here, one hits this way and the other one has to go this way. But what happens if one of them is dark matter? Well, I don't see that particle anymore because it goes right through my detector and out into space forever because it doesn't interact with light. So I have these two protons come in, they hit each other, and everything I see comes out this side, right? Nothing goes this way. And so I see, wait a second, I must have missed something going the other way because I know how particles collide, just like billiard balls, really. And so I say that must be a dark matter particle that I missed. And if you look, and if at certain energies you're missing more particles than others, you say, hey, there might be a dark matter particle that has that amount of energy in your collision. So this is done as a very difficult measurement, because really I'm just looking for, hey, I missed something. And finding that you missed something is a very difficult thing to do, instead of actually seeing something. You can do direct detection, which is you go and you make basically a big jug of water or silicon or something like that. A dark matter particle comes in from space. There are millions of dark matter particles. I put the number up here somewhere. 100 million every second going through you right now. And then it goes through our detector, and because there's some weak interaction, it's not very strong, thus the name, we're creative. There's some weak interaction, it can sometimes bump one of the atoms that is inside your detector, and then you can see that atom wiggle. And maybe you set up your detector so that when atoms wiggle, it makes light or it makes heat or something like that, and you detect that light or heat. So the way you do this is you go really deep underground. The reason you do that is because on Earth there are things like cosmic rays coming from space that hit your detector all the time. And you don't want to just be recording when other high energy particles come from space. So what you do is you go under lots of ground. And the high energy particles coming in from space hit the ground and they lose energy in the first layer of the ground, basically. Just like you want to put on sunscreen so you don't get radiation from the sun, same sort of thing. So you go deep underground. The dark matter mostly just passes straight through the Earth, so it can get as deep as you want it to, but nothing else from space can. So this is Sudan underground mines in Minnesota. It's an old gold mine that's 5,000 feet or so under this boring area in the middle of Minnesota. Or you can go to ground Sasso labs if you're lucky, because when you get to go back up from your 5,000 foot deep lab, it is much prettier. This has its own dangers. My friend was actually in charge of manning his experiment at Sudan labs to look for dark matter when the labs caught on fire, because it's an old mine with lots of coal dust and other stuff in it, and the mine shaft itself caught fire. He was actually above ground, but he was turning off all of his experiments and trying to make the electronics not short circuit and all those sort of things. So they're kind of dumping fire retardant chemicals down the line. He said it was his most exciting 20 minutes in physics. So, and this has a local flavor, which is worth pointing out. So there are probably more than a dozen dark matter direct detection experiments. They're relatively low cost. One called Cogent uses silicon. This is being held here by Juan Colliar, who's a professor here at the University of Chicago, and is the head of that experiment. And they have these little bits of silicon that make electronic noise, basically, when you hit them in dark matter. There's an experiment called LUX, which uses this huge tank of liquid xenon, which is a cold liquid element. There is what's called a CDMS, which uses Sudan Labs, which I just pointed out was the experiment my friend was working on. It has a lot of people at Fermilab working on it. It's one of the centers. And then there's the COOP experiment, which uses a chamber filled with a type of liquid waterish substance called the Chicagoland Observatory for Underground Particle Physics. And so that is mostly Fermilab and Chicago people. So quite a bit of local flavor. The last thing you can do, that was called direct detection. And the reason we call it direct detection is you're actually seeing the dark matter particle hit a particle on the Earth, and you're just recording how that interaction happened. There's also what's called indirect detection. And that's looking for two dark matter particles. This is what I'll talk about for the rest of the lecture here. Two dark matter particles, they hit each other, and they produce visible light or visible particles like electrons or protons that we can see. And what you don't see is the dark matter interaction itself. What you see is a new signal of light where you didn't expect it, somewhere in space. So to do this, you want some sort of telescopes This is the Fermi telescope that I work on directly, which is a NASA space telescope. Orbits about 400 miles above the Earth, and it looks for very high energy light called gamma rays, which is just, our visible light is, these gamma rays are about a billion times as energetic, each photon, as the visible light that you can see. There's other experiments. This is Veritas, which is in Arizona, and it actually looks for gamma rays too, but it goes from the Earth, and what it looks for is a gamma ray enters the atmosphere, and it has such a high energy that the gamma ray produces this huge shower of electrons, and it looks for that shower of electrons going through our atmosphere. It's a pretty cool experiment. There's AMS, which is hooked onto the space station now, and it looks for high energy like electrons that are hitting near the Earth, and some of those could be due to dark matter also. So what are the newest results for each of these experiments, or each of these different methods for finding dark matter, right? They're complementary in that they look for different types of dark matter in different ways, and so we try to use all three. Well, LHC, as you probably heard, observed the Higgs boson at 125 proton masses about a year and a half ago now. So that's actually a decent hint for supersymmetry, because to get a Higgs that's 125 proton masses, you actually need supersymmetry. This is the particle physics reason for having supersymmetry. And the supersymmetry particles can't be too much heavier than 125 proton masses. They can't be more than, say, 1,000 proton masses or something, or some theoretical stuff I won't go into goes wrong. The LHC, on the other hand, can accelerate protons up to 14,000 proton masses. So there's a good chance when it turns back on and gets to 14,000 proton masses, it will be able to see these kind of supersymmetric particles. And maybe one of them is the dark matter. In direct detection, you're not supposed to show a plot like this because the situation is a mess. You don't have to interpret this plot, except everywhere you see these kind of blue or yellow shaded regions is where a group claims that they have detected dark matter. So you see yellow here from this DAMA experiment, you see brown from this CREST experiment, blue from the CDMS, blue from the CDMS experiment, purple from the CoGen experiment. Wow, we have lots of dark matter detections. Unfortunately, none of them agree with each other on where the dark matter is. And then all these lines you see are groups that said, well, the dark matter can't be anywhere above this line. And as you can see, this is a problem because this says that this can't be true, but this says this can't be true, and that says that can't be true, and that says that. And it's a mess, but it's also interesting, right? Because it means that we're getting into an interesting place where clearly some experiments are not quite working correctly, and we need to uncover that. But it's now an experimental issue as to whether there's any dark matter here or not. So this has been kind of slowly being sorted out over the past maybe 3 or 4 years, and it's going to continue to probably be sorted out over a year or two. So it's interesting, super interesting, but also kind of a mess. So indirect detection. Indirect detection is an important one, and I say that mostly because that's what I do. But indirect detection is important because that's what tells you that the dark matter particle is actually in space, where dark matter is supposed to be making galaxies spin. Right? If I produce it in a collider, I know I produced a new particle that doesn't interact with light, but I don't necessarily know that that's what makes up most of the universe's dark matter. I produced a particle that has all the right properties. I don't know that that's actually a particle that's in space by the tens of trillions of billions of particles. Indirect detection, if I see that in the interactions, it tells me that's what's actually in space. And so I will show briefly. This is a plot, and what you can also do with indirect detection is you see this horizontal line here. You don't have to interpret this plot too much. This is how much dark matter, how likely dark matter is to collide with another dark matter particle in space. It should make this line, and this line is important to make the correct amount of dark matter that we see in the universe. It has to lie right on there somewhere. And this solid line here is where we say the dark matter can't interact more often than this line. Can't be above this plot on the line. And you can see for low dark matter, very light dark matter particles, this line is starting to cut through the dashed line, which is good. That means that dark matter particles that are at these very low masses can't be the dark matter because they don't collide enough to make the dark matter we see in the universe. So a little bit of a technical plot. This was actually done by looking at very faint things called dwarf galaxies that have lots of dark. They're in the Milky Way. They're little kind of substructure things, or they're basically sub-galaxies in the Milky Way. And they have lots and lots of dark matter, but not many stars. So almost everything you see should be dark matter. And so you should see high-energy photons or high-energy light coming from them. And if you don't see it, then you say, well, the dark matter can't interact very often. It has to be below some amount of interaction. And if that goes too low, then you can't form the dark matter in the universe. Great. So we're starting to rule out actual models. This is really great because 5 years ago, people still made this plot. And theorists would invent ways to make dark matter brighter and brighter and brighter so that you could rule out the models, right? You always want your theory model to be right below whatever you can test right now so that it's exciting because you can test it soon. You don't want a model that's way down here because I don't know how to test whether that model is true or not. So it used to be that we're inventing ways to make dark matter brighter and brighter so that we could test it with experiments. Now the experiments are getting so good, we're starting to make ways to make our dark matter dimmer, so that you can't test it with experiments yet, right? So we're at an exciting time. This is another plot that shows kind of the same thing. I'm not going to actually go into it. So another experiment, the project I've actually been working on recently, looks at the Galactic Center. So the center of our galaxy, there's a lot of stars there, a lot of things that make high energy light, like gamma rays, but there's also supposed to be lots and lots of dark matter. So what we do is we take a look at the center of our galaxy using this Fermi telescope. This is the actual sky here in Fermi. You see the galactic plane, basically the kind of plane structure of our galaxy is very bright. This is the brightest thing in gamma rays that makes this plane. And in the center of it is the center of our galaxy. And you try to look at this image and you remove all the things you know about. You remove the gas that makes gamma rays, and you remove the very dense stars and black holes that make gamma rays. You try to take those all out of your image and see what's left. And you could set constraints. You could rule out dark matter if there's nothing left, because there's supposed to be lots of dark matter there. And what happened was we took out everything that we know about, and what we see is this bright blob that's left. This kind of circular blob, which looks, dark matter is supposed to be kind of a sphere around the center of our galaxy. Side. So here's the full image of the center of our galaxy with all this extra stuff in. This is a bright neutron star that we know about. This is another bright neutron star that we know about, or a black hole or something. And we remove all these things, and what we get left is this very bright thing in the center of our galaxy that looks a bit like dark matter. And NASA actually made a cool movie of our discovery, which I will show you. So here's the kind of our galaxy, this plane of our galaxy. We're zooming in on the center. And right now this is just a Hubble image, because Hubble makes really pretty images, so they use them. And as we get closer and closer into the center, they're going to suddenly juxtapose our gamma ray map on. Here's our gamma ray map, and now they're pulling apart all the known emission, and here's what's left. So this is what the center of our galaxy looks like on top of this Hubble map in gamma rays. And we said, what does the spectrum of these gamma rays look like? What does it look like something that dark matter is supposed to produce? And it turns out, I'm really excited, it does. So here was a line for what we thought dark matter would produce in terms of how much energy should these different photons have. And we made all these. This is our measurements. And it fits this line very, very, very nicely. So we're excited. And another group did the same thing and found the exact same thing we did. And so now we're really, really excited. It's actually got a little bit of press recently, just in the past maybe 3 weeks or so. It was in The Guardian here. I think this is Time Magazine. And it was the front page of NASA for about 47 minutes or something. And then they found water on a moon of Saturn, and that was way cooler. And so it got replaced. But we're looking now with three different kind of ways. We're looking with colliders. We're looking with these kind of underground observatories. And we're looking out in space. And we're seeing if we find dark matter. And this is a fairly strong hint that we might actually be seeing something. It's pretty exciting. Other groups are going to look, more carefully. Maybe they'll rule it out. Maybe we did something wrong, or maybe it's some other thing that also makes high energy light, but we've never seen before, which would also excite me, just not quite as much. To conclude here and give some time for questions, the observation of really fast-moving stars and galaxies led us in a really interesting direction over the past 80 years. Not the direction we thought we were going to go when we said, hey, that star, it's moving kind of fast, don't you think? And it tells us a lot about how the universe formed and how the universe is created, what the particle physics of our universe is, etc. like that. But we still don't know what the dark matter is yet. We know it's out there. We know it influences how galaxies form. We know it influences how stars move around galaxies. We know it influences this cosmic wave microwave background light that we see everywhere. Cosmic microwave background light. But we don't know what the particle is yet. But right now, we're just reaching the sensitivity with all these instruments that we're really probing what the model is supposed to be, right? We had our, when I used to say we used to do all these things to make dark matter easier to see. And now we're at the point where we're writing down what you learned in grad school dark matter was supposed to look like. We're now looking at those models, not the ones we were making artificially easy to see. So we're in a really exciting time, and hopefully a lot will come out in the next couple of years. So thanks for attending. Thanks for your attention.
Do galaxies clump because dark matter itself clumps?
Yeah, the question for people who didn't hear was, does dark matter cause galaxies to clump? Is it dark matter that's clumping and causing galaxies to clump? And that's exactly right. So dark matter, what happens in the early universe is that some areas have a little bit higher density than other areas. And over time, matter falls into those denser areas due to gravity. And because dark matter is most of the mass and most of the matter, that happens earliest for dark matter. And so it forms those kind of spiral webs that you see. And everywhere that you have a high mass, all the other matter falls into that area too, because of gravity. Gravity is a very weak force, but because all particles attract each other, so for something like electromagnetism, for light, you can repel two things, or you can attract them. And over large distances and many particles, those cancel out. Gravity always attracts, so on large distances, and for very big masses, it's the strongest force, effectively. Yeah?
So if dark matter is the answer to the question why galaxies formed instead of having a uniform distribution of visible matter after the Big Bang,
Yeah.
does this raise the question of why is dark matter clumped in structures rather than uniformly distributed after the Big Bang?
So, okay, so let's pretend there was a new universe with no dark matter. Things will still clump towards regions where there is more mass. So if we just had the matter we could see today, we would still have some clumps and galaxies would form at the center of those clumps. But because dark matter has most of the mass, the properties of dark matter are what control how the clumps form and where they form. So dark matter itself, everything itself that has mass will clump in regions and produce regions that would have something like a galaxy in them. But dark matter is the most important part of the clumping. And so the properties of how dark matter clumps, which are different than how, say, normal matter clumps, is what controls the clumping that we see.
So it's incorrect to say that you would expect a uniform distribution of matter or dark matter from the Big Bang.
Right, yeah, there will be some clumpiness either way, but the clumpiness will be very different if you do have or don't have dark matter. Yeah, in the back, right?
And historical note regarding the expansion of the universe. I thought it was the astronomer Sleaford who discovered the expansion of the universe and then turned the information over to Hubble, who was known as a very precise measurer.
That is true. People did trust it because Hubble measured it, and he's famous for such things. I don't, sorry, 1929 is slightly before my time, so I don't remember if that's true or not. You can actually see this data is really bad. Like, people trusted it because Hubble said, oh yeah, that's true. And he was known as the best. But like, I could draw kind of a straight line through that too, right? Like, there's not too much of a slanted line. Now the data is really, really, really good. We have, instead of like 50 data points on this, we have like a billion data points on this, and we have better measurements of all of it. It all lines up. But at the time, it was quite a trick that Hubble announced, and it was true. Yeah.
Hubble had a better telescope.
Oh right, this is the answer. He thought it was true, and Hubble had the telescope. Now I remember the story. Thank you.
In the underground direct measurement, how do you differentiate a neutrino interaction from a dark matter interaction?
Good question. Very good question.
What was the question?
How do you differentiate when you go underground, dark matter goes straight through the Earth, and neutrinos also go straight through the Earth and come out the other side. So those should both hit in your detector, and they use the same weak force, which you probably know. And so how do you differentiate those two? And the reason is that neutrinos are very light, and the dark matter we think is very heavy. So most of the neutrinos, they will collide, but they will produce very, very tiny wiggles in our detector. And you won't see the neutrino wiggles because they're so small. The dark matter ones are supposed to be bigger. Let me zoom out here, maybe. I will. So on this plot here, it turns out that once you get down, this is a small number, 10 to the minus 43. Once you get down here to about 10 to the minus 48, you will start seeing neutrino wiggles all the time. And that is actually kind of the end of direct detection. If it's not at least this bright, you won't see it because you won't be able to find out what's a dark matter and what's a neutrino. So it's something people worry about nowadays. Well, people worry about in 2030, I think, is when we expect to have an instrument that's sensitive. Yeah.
Since the Big Bang inflationary theory was developed without the concepts of dark energy and dark matter and did not predict the increasing expansion of the universe, doesn't that theory then need to be revised from the beginning?
Need to be revised. So the Big Bang itself is kind of based on a simple premise, and that the universe was expanding at some speed. And if everything is getting farther apart, you just go back in time and everything's getting closer together. And at some point, everything had to be a point. And I should clarify, no one believes that at one point the universe was actually a point singularity. Eventually the universe gets so hot and dense that we don't have physics that describes how things that are very, very, very hot, very, very, very dense work. And at that point we need a better theory for how the universe actually began, and we don't have that yet. But yes, what the increasing acceleration of the expansion does is it tells us we have to go back in time differently, right? So it changes how old the universe is slightly. So how much, how far you have to go back in time to get to this point. It changes changes a little bit about how you do this expansion over time.
Okay.
But overall, the theory itself is still basically the same. The going back to a point is still the same.
Thank you.
Yep. Yeah. Yeah. Sorry. You can't go.
Is dark energy what is believed to be what's pushing the universe apart?
Yes. Dark energy is this extra 73%. The way to think about dark energy or dark matter is that things have a mass that pulls things together, but they also have a pressure that pushes things apart. You know, if you turn on like like an air pump, right? It pushes air out and that forms a pressure and it pushes everything apart. Dark matter and regular matter are things that have much more mass than they have pressure. So the mass pulls things in more than the pressure pushes things out. And dark energy is the opposite. It has more pressure than it has mass. So having dark energy, like a dark energy, we don't know if it's a particle or what it is at this point. It's much more uncertain than dark matter. Having dark energy pushes things apart more than the mass from dark energy pulls things back together. And so that causes an expansion of the universe. Yes?
So the Earth, just gravitationally, should have dark matter, presumably at the center. What fraction of the Earth?
Very, very small. So the ways to think, so dark matter, and when I talked about stars moving around galaxies, I was talking about the stars that were on the very outside. And I can go maybe back and show that if I remember where it is. It's right here. So if you notice, in the center of the galaxy, these two curves aren't too far off. That's because most of the mass right at the center of galaxies is actually the stuff we can't see. Stuff like stars and that. And the reason for that is that stars can interact with light, and when you can interact with things, you can cool some of them. So two gas particles can hit each other, they do a lot. One gas particle slows down and it falls in towards the center. And normal matter can do that, dark matter can't. So dark matter tends to clump much more densely right at the center of galaxies than dark matter, which is actually a little bit more dispersed. And so it's out here where dark matter is creating most of the mass, really far away from the centers of galaxies. So anytime you have something really dense in normal matter, like the Earth or us, it's mostly normal matter, and the dark matter part is very small. So there is the local density, basically how much dark matter is near us today, is about 1 particle per 100 cubic centimeters. Whereas or like 1 proton mass per 100 cubic centimeters, and in this wall there's 10 to the 20 proton masses per cubic centimeter. So, yeah. In the back.
Since dark energy pushes forces away from each other, is it possible that somehow dark energy could help cause the Big Bang?
Possible. I think there are a lot of theories. There are a lot of theories about how a Big Bang occurred or how things would move apart, and I don't work on them much myself or get into them much. It's a good question, and the real problem is when things get really, really hot and really, really dense, eventually physics doesn't work anymore. We know that there are new ways that particles can interact at really high energies. Not like high energies that we can make in a particle accelerator, like a billion times those amount of energies. We know that there are new interactions, and we don't know what they are. So there's possible that there's tons of new particles there that do something that we don't know about. And in fact, that was one of the things that was found in this BICEP experiment that you probably all heard about because it was front page New York Times. I told my friends, so actually, it's a fun story. BICEP, has a couple people in Chicago who work on it. And one of them was like, we got a lot of headlines. And I said, a lot of headlines? You were front page above the fold on the New York Times on a day Russia took over another country. So anyway, BICEP found this inflation, this really fast expansion of the universe in the first a billionth of a billionth of a billionth of a billionth of a second after the universe was formed. They found this rapid expansion. And that was caused, we think, by a new particle that has a mass that's a billion times higher than masses that we could probe on Earth, called an inflaton. It inflates things, inflaton. We think there are new particles there that probably do this early expansion of the universe, but we don't really have a theory that tells us what they are. Yes?
Yes, the gravitational constant of Newton, is there any speculation whether it is the same for dark matter as visible matter, or it might be totally different?
Yeah, another great question. And what I can point to, if I can make my slide show go there, is that bullet cluster observation. So one of the things that was a competing idea to dark matter for a long time was maybe there is a modification to Newton's gravitational constant for everything. Or Einstein's relativity really is the one you would use. And we don't actually know how the gravitational constant works along distances or for different types of matter or something like that. But the key insight is really that this dark matter moved to a different spot, right? It's not located at, you don't expect the center of the mass to be not where the mass is. So that's what really pointed us in the idea that this is the same sort of particle. And if you put a new particle in, then everything works with the same Newton's constant, with a very, very nice theory that predicts things like how galaxies form. So at this point, there's no reason to expect that, although you could certainly write down a theory. Yes?
So with the idea of the expansion of the universe due to dark energy, is it correct to infer from that there's more energy in the visible universe today than there was a year ago or 10 years ago? And if so, is this an observation that should be said to falsify the principle of conservation of energy? And
Good.
is
Great question.
energy coming into existence, and if so,
Yeah.
from where?
Right. The key statement in that is in the visible universe. I should also mention, if people need to leave, we're after 12:05. I can keep answering questions, but if people want to leave, I'm not offended if you need to go. But in the visible universe, we don't know that everything in the entire universe is visible to us. So there is a very rapid expansion in the early universe. And if that rapid expansion continued, and it did, there would be things that started so far away that light from those objects never got to us. It's part of the universe, but it's not a visible part of the universe. We would never see it. And so you would see that, right, with the expansion of the universe and if it's accelerating. Finally, things would get so far away from us that you would never see light from them ever again. So we expect that the full universe is, we don't have to scale for it. It's much, much bigger than everything you can see in the universe. So when you're expanding space, you are, in fact, sort of adding energy density because you're adding new space. You are also adding negative gravitational energy, to answer your question, and those two cancel out. So it turns out conservation of energy is fine in the way that you're adding an energy density, but you're also moving things apart from each other, which decreases their energy of attraction to each other. And we don't know how much gravitational energy there is basically in the full universe. It's actually quite possible, and when I like numbers being zero if they can be zero, it's quite possible that the total amount of total energy in the universe is zero, with lots of energy in everything we see today, and lots of negative energy in how things are separated out over very large scales. Yes?
I've read a number of times that for inflationary theory to work, the inflation had to occur faster than the speed of light, and that scientists then say, well, that doesn't violate the special theory of relativity because space is in light. And isn't that kind of a sophistry? I mean, getting around a contradiction between the two theories?
So what, yeah, I don't think so. So what Einstein's theory, special relativity, says is that no signal, light, or messenger can move faster than the speed of light, which is constant in every single what you call reference frame, or for every single type of observer. So if two objects move farther away from each other than the speed of light, then they can't exchange information between each other. There's no particle or that can travel between them that can make up that distance, that difference. So a way to think about it is this. Hopefully I hit this, so I hopefully didn't shine on you. I can do this, like I just did, right? And let's say I did it out at the night sky. I have light that was moving at some speed. And if I get farther and farther away from me, say out at Andromeda or something, the fact that I moved this light beam very fast across Andromeda, right? Like it went across all of Andromeda in like a second, because Andromeda is just this little bit out here, and I moved through it. I had something that moved faster than the speed of light across Andromeda. I mean, I could write down how fast did this beam of light shoot across Andromeda, and it's faster than the speed of light, but it wasn't exchanging any information. Like, you know, no observer over here would be able to know that that light beam was moving faster. So the key thing is you can't move information in any way faster than the speed of light, whether that's via a light beam or a neutrino, or making a gravitational shake that someone can see. None of that can move faster than light, but like you can conceptualize space or other things that propagate at fast speeds.
Thank you.
Yep. Way in the back.
If the universe is expanding, why don't the galaxies within the galaxies expand?
So, good question. It's how much dark matter is there? And I said, remember, dark matter has more mass. It pulls things together more than it pushes things apart with pressure. And dark energy has more pressure. It pushes things apart more than it has mass that pulls things in. So a region that has a lot more dark matter, or has a lot of dark matter or normal matter, on average pulls things together much more than it pushes things apart. But an area that doesn't have much matter like an area in between galaxies that's mostly empty space, has a lot more dark energy than it has dark matter, and so things mostly move apart. So it's just how much mass, how much pressure overall. Also in the back corner.
You said when things get so hot, the laws of physics don't operate. Is anybody thinking about that, coming up with any theories on what is happening? And also another question, is this the first universe, or I've heard somebody say, well, it's just the most recent one in an infinite series of universes?
Right. So these are questions people ask a lot and think about, and especially after this BICEP result, because this result was, I can't overstate how important it was. It gave us the earliest thing we know about the universe, if it's true, which will hopefully be confirmed in the next couple of years. And so actually in the past 3 weeks since BICEP, I think 160 papers have been written on things that happened in the early universe at this new physics scale. So people do think about that all the time. The question is observations. I can write down 1,000 different theories about what happens at these energy scales. And that's easy work if I don't have an observation that can tell me if it's right or not. And there's a question, if I write down a theory that will never be tested observationally, is that physics anymore? If I can't possibly think of a way that's tested. Which is a little bit the second question too. Are there universes before ours? I don't know how to do physics before there was the Big Bang and before there was time or something like that. So my choice is generally not to try to do that. But people have thought about this, are there multiple universes? Did they collapse and then expand again or something like that? That actually looks less likely since the acceleration of the universe is actually, or the expansion of the universe is actually accelerating. But there's this idea that inflation, this rapid period of expansion of the universe could actually go on forever. And so we are in an area of the universe where there was inflation, and then inflation stopped, and then the universe collapsed into galaxies and formed. There would be some area that we would never see because it's very, very far away from us now because inflation expanded things apart, where inflation is still happening. And when inflation stops over there at some point, a galaxy will, or a new universe will form. And because so much expanded between those, we will never see each other. So it would be like there was a whole other universe. This is kind of the multiverse theory. And people debate, is this philosophy? And the response is it's actually very hard to write down an inflation theory that does not lead to inflation that goes on forever. And the reason for that is there's a kind of a probability at every point in time that inflation will end. And so maybe in this spot of space, inflation ends. But because inflation is making much more space at a really, really fast rate, there's much more area where inflation didn't end. The area, the small part where inflation didn't end, it inflates and becomes a lot more space. And that just keeps going on forever. And so it's interesting. I don't know that we do or will ever have an answer to that. But for the first time, this new observation gives us an idea that maybe we will. Yes?
Given that the expansion is accelerating, is it true that we in the present are leading the acceleration?
Are we leading it?
Pardon?
You said leading the acceleration?
Are we moving the fastest? Are we accelerating the fastest? Because we're in the present.
Right, right. Good question, and it brings us back to this cosmic microwave background. When you say if we're expanding the fastest, then we would be expanding in some direction. We'd be going this way or that way. And what that would do for the cosmic microwave background, because we would have some velocity now in some direction, is it would make the light that we're going towards would redshift, right? From this slide back here, light in one direction would redshift more because we're moving away from it, and light in another direction would blue shift because we're moving towards it. And so if I looked at this image here, I would see a really red area over here and a really blue area over here because we're moving in some preferred direction. So the best way to think about it is that there is really no center. And every point is moving away from every other point equally. And this is kind of this balloon analogy. if you start with a balloon that's deflated, and imagine you could deflate a balloon all the way down to like a single point, and you started expanding them, what is the center of that balloon? Every point is moving farther away from every other point on this surface, but there's no center point that's preferred. And that's how we think the universe works. Is there some, and you guys, I'm just seeing if there's anyone new. Okay.
So if the mathematical limit of turning the clock backwards is a point, and you said no one really believes that the universe consisted of a point, am I misunderstanding Hawking then about the beginning of time and the brief history of time? I thought that his saying that time had an origin came down to saying that it was at a point.
Yeah, I prefer the term cosmic egg, I think, where we know what, if you take our observable part of the universe back, we know actually all the way back to when it was like the size of a marble. Or our laws of physics at least work back that far, which is really impressive. But beyond that, that's close enough to a point, actually, in talking about like the whole billion-year history of the universe. But that first 10 to the minus, 30 or 10 to the minus 40 seconds, is a bit of a mystery. And so, for simplification, you can think of it as a point if you're thinking about the whole universe. And I think at some points, a lot of physicists do that. Singularity, just, I can't define how physics works at a singularity. So I don't know that that's true or false. But I think, it's probably a generalization to think of it as a point because it's close enough for most of the things you talk about. I'm going to do one more, and then I'm going to start taking questions, but I'll be down here for another 20 minutes or so if people want to come by. Yeah?
Does the dark matter have to be material? Like you mentioned that it can't really be explained with different laws of physics, but could it be, for example, explained with like lumpy space, for example, and like the bicycle?
Yeah. Good question. I think again, I would go back to that kind of bullet cluster observation, where everything we know that has mass has been a particle. And actually, if you just go back to straight throw keywords in quantum field theory, if you have a theory of how particles work, everything has to be a particle. You can even describe sound waves in terms of their particle properties. We think everything that has mass or exists really is due to some sort of particle. We know that those particles, or whatever you call them, maybe waves, travel differently than the normal matter do to a specific point, which is why we think it's something new. I only talked about what I call weakly interacting massive particles, these kind of WIMP particles that are 100 times the proton mass and interact via this weak force. There are other models that make up the dark matter. One of them I didn't talk about is called axions. There it turns out they are particles, but you think of them more in terms of waves because the particle is dispersed over like thousands of light years. So there's some things are waves and some things are particles. You can describe them as in both ways. For these particles, they're very heavy, and so they're concentrated, and you think of them as particles. For axions, they're very low mass, so they're diffuse, and you think of them as waves. But this is sort of okay, thanks everyone again for coming.